Friends, welcome to the lecture 39 on Advanced Steel Design course. We are discussing about the shear center, so we will call this lecture as Shear Center 2, because in the last lecture we discussed about the conditions under which twisting of cross section should happen, and we stated clearly that if the load is applied or passed through the shear center, you can avoid twisting of the cross section. Therefore, friends, shear center is a geometric point in the cross section, which is actually the intersection of the loading plane with the bending plane. Okay, this is what we said. Furthermore, if I have an angle section as shown in the screen now, we already know that the internal force distribution will be as F2 and F1. If you apply a force V and F1 and F2 intersect at the point A, so one can say that F1 F2 intersects at the point A if the load is applied or the line of action of load passes through the point A, then one can avoid twisting of the cross section. Okay. We already said that shear center is the intersection of the bending plane and the loading plane. We can also define shear center in a more geometric sense. Let us say I have a cross section of some shape. This is my point of action W and this is the shear center offset E from the CG, and we have applied a load V. Therefore, friends, shear center is a point of intersection of the longitudinal axis of the member, that is this axis, and the line of action of the transverse load. Which is point C. So, therefore, friends, shear center is a geometric point, whereas mass center is identified as CG. If the load does not pass through the shear center, then the section will be subjected to twisting moment. So, we can say straight away here, for E equals 0, okay, no twisting moment. Now let us quickly see where are shear center very important in what kind of structures. Let us take for example marine structures. We already know marine structures are strategic structures constructed for specific functions. Usually they are constructed, or I should say fabricated, because we use essentially steel as a material using thin walled elements, and sections are also chosen to be asymmetric. Therefore, under such conditions, the cross section will fail in torsion, because it will be weak in torsion before it fails in bending. So, this twisting will induce a premature failure of the members. So, that is a very important status. So, therefore, shear center or location of shear center are important in such kind of structures where they are thin walled elements and the sections are asymmetric in nature. Okay. Furthermore, this will also cause warping, which will induce geometric instability, and which is one of the most undesirable characteristics in design. Okay. Friends, shear center location is made comfortable by a simple logic. Shear center will coincide or will lie on the axis of symmetry. If a section has two axes of symmetry, then their intersection will be the shear center. So, sometimes in most of the sections, shear center can be located by simple observation. Okay. We can show some examples. Let us say a rectangular section where there are two axes of symmetry. So, this becomes my shear center. A tubular section which is commonly used in marine structures where there are at least two axes of symmetry, that becomes the shear center. If I have a T section which has one axis of symmetry, shear center will lie on this axis. Okay. Now the question comes, where are asymmetric sections popular? You must have seen in crane rail. Crane rail has a section like this. This becomes my crane rail. This will have a cushion effect here. And this is what we call as a slip gap. And this is the freeboard. So, if the rail jumps off the crane, rail bends, still the wheel should not touch the top. Okay, this is a typical cross section of a crane rail. This is a classical example of an asymmetric section. So, in heavy industrial structures, friends, you will see that asymmetric sections are very commonly used as load carrying elements, which are also crucial elements in the whole setup. Having understood this, let us try to derive the basic equation for finding the shear stress. Let us say we have a flange of a channel section of depth d and breadth b and thickness t. We know that this section has an axis of symmetry. Shear center has to lie on this axis. Okay. Let us imagine this along its length. Okay. At a distance x, let us cut a strip. Let us say at a distance x, let us cut a strip. So, I am drawing that strip in an enlarged view here. Okay. Let us say this is my plane of reference. Thickness Bt, let it be cut at a distance x and a strip is being cut of thickness dx and area of this hatched portion is dA. Okay. And let us say we have an axis which is measured as B distance from there, and along this axis we have H and we have M acting in the cross section. Okay. Now I want to find the shear stress in the flange. Now H will be given by m by I into y of dx, dA x to b, equation number 1. H plus dH will be m plus dm by I into y dA, which will also run from x to b. Equation number 2. Equations from first principles. Okay. Now I want to find the unbalanced force along the length is given by equation 2 minus equation 1, which will be dH, which will be x to b m plus dm by I y dA minus integral x to b m by I into y d. We call this equation number 3. Now I can say it is dm by I into x b y d. Equation number 3b, we will call this 3a. Now for equilibrium, this unbalanced force as given by equation 3b should be equal to the elemental shear which is opposing this force. Okay. Let tau be the shear stress. Then the elemental shear force will be tau times of T dz. So now for equilibrium, this should be equated dm by I integral x to b y d. So now I can say the shear stress is going to be dm by dz 1 by it integral x to b y d, which can be dm by dz 1 by it ay bar, because y dA integral is ay bar, whereas tau is now going to be v a y bar by it, where v is the total shear at the section. Ay bar is the static moment of area. I is the moment of inertia of the whole section, and T is the width of the section, okay, perpendicular to shear. Having said this, let us try to do a problem to locate the shear center for a section. So, we will say example 1, locate the shear center for the given cross section. Let us draw the cross section. Let us mark the geometric dimensions of this. Let us mark the center line of this. Call this dimension as h, this thickness T1, and this thickness T2, and this breadth as B2, and this breadth as B1. We also know that this line is automatically the axis of symmetry. Let us assume that the shear center is located here. Okay, where the external load V is acting to avoid twisting of this cross section. We call this distance of offset as E1 and E2. So, our job is to find either E1 or E2 because they are connected by a relationship. E1 plus E2 will be equal to H. Let us take this thickness of the section as T3. Okay. So, this is my first element. This is my second element, and this is my third element, where the intersection is cut here. Okay. Let us say the proportional shear shared by the flanges 1 and 2 are indicated as. By the way, we know that they are flanges. And this is called as a web, or indicated as V1 and V2 respectively. So, we assume that the total shear V is counterbalanced by these two shear. So, we are neglecting shear are counted by the element 3. Okay? So, now let us cut a section at a distance y of thickness dy and the area shaded is dA, and this is the part above the section under consideration. This part has a CG, let us say that is y bar from here, from the axis of symmetry or from the line where the shear center is being located. Okay. Now, tau is V A y bar by I t, this known equation we just now derived. Let us put it a small a. So, the small a for the component 1, this is for element 1. Okay, component A is going to be B1 by 2 minus y. Okay, that is the hatched portion in cyan color. Okay, B1 by 2 minus y into T1. Let us say y bar is y plus B1 by 2 minus y, half of that, which will be y minus y by 2 plus B1 by 4. So, I can now say y bar is y by 2 plus B1 by 4, because we need y bar here, we need a here. Okay. Now, I can substitute tau of member 1 is V A y bar by I t, which is V by I T1. A y bar is just now we computed, which is B1 by 2 minus y of T1, and y bar is y by 2 plus B1 by 4. Let us simplify this. Tau of member 1 will be V by I T1 of T1, B1 by 2 minus y, half of B1 by 2 plus y. Can I write like this? Because I get a product here, okay, A minus B and A plus B. So, which can be V by 2y as T1 goes away, 2y of B1 by 2 B1 by 2 A square minus B square. Equation 3. This is my tau of the first member. Okay. So, therefore, I can write V1 is integration of this, of the whole area, varying from minus B1 by 2 to plus B1 by 2. See this figure? Minus B1 by 2 to plus B1 by 2. That is from this section here, from this section here, is it not? So, that is the validity of the shear force V1, which is shared by the flange 1. Okay, let us substitute and find out this value, which will be 2 times of 0 to B1 by 2 tau of 1 dA because of symmetry. So, which will be 2 times of integration 0 to B1 by 2, tau 1 we already have. So, V by 2I B1 by 2 the whole square minus y square, okay, of dy of T1, is it not? That is the strip area which is integrated from minus to plus limits of this, am I right? That is dA, okay, that is dA, that is dA, okay friends. So, we will simplify this equation. So, which will now become 2 Vt1 by 2I of integral B1 by 2 B1 by 2 the whole square, sorry, let us do it, B1 square by 4 minus y square of dy, am I right, which is going to be V T1 by I B1 square by 4 of y minus y cube by 3, limits varying from 0 to B1 by 2. Substituting, we get Vt1 by I B1 cube by 8 minus B1 cube by 3 times of 8 which will be V T1 by I B1 cube by 8 minus B1 cube by 24, which will be V T1 by I B1 cube by 12, which is V1, okay. So, I can now say V1 is V T1 by I B1 cube by 12, which can be rewritten as V by I of I1, am I right? Please see the figure. What is moment of inertia of piece number 1 about the axis of symmetry? Is it T1 B cube by 12? So, that is what I am having here. So, I have replaced this as I1. So, I can now say V1 is V by I of I1, equation 4. By the same logic, I can apply this to piece number 2 or flange number 2. I will get by the similar logic V2 will be V by I of I2, equation 5. Okay. Now, we have two equations. V1 is V by I1, V2 is V by I2, where I1 is T1 B1 cube by 12 and I2 is T2 B2 cube by 12. We also know total shear is sum of these two, shear taken by member 3 is neglected, we already stated that. So, the total force shear will be V I1 by I plus V I2 by I Okay. So, that is the control equation we have with us. Now, let us take moment about the point C. See this figure, I will copy this figure. Okay. Now, let us say we will take moment about shear center C. So, V1 into E1, which is clockwise, okay, this is V1, this is V2, should be equal to V2 into E2, which is anti-clockwise. So, what is V1? Please see from this equation, which is V I1 by I of E1, and V2, see from this equation, I2 by I, is it not? V I2 by I of E2. So, from this relationship, we get a concept I1 into E1 is I2 into E2. We get one relationship from here. We will call this equation number 6. Sorry. Also, we know that from the geometry, E1 plus E2 is H, is it not? See here. The solving equation 6 and 7, because we know I1 and I2, we already have them here. See, I1 is known, I2 is known. So, I already have I1 known, I2 known. So, there are two unknowns, E1 and E2. I have two equations. So, by solving equations 6 and 7, we get E1 and E2, and I can locate the shear center. That is a very easy approach. From first principles, we found out the shear center very easily. Yes, friends, it is a very easy illustration for applying the fundamental logic to obtain the shear center. Okay? Let us apply onto a problem and see this quickly. So, we will say the same dimension, I will just copy this figure again. Okay. Let me give these dimensions as B2 is 100, okay, I will write in a different color, maybe 100, which is B2. B1 is 50, T1 is 10, T2 is 20, and H is 80, all dimensions millimeters. So, we have an equation E1 by E2 is I2 by I1. Can I have this equation here? E1 by E2 is I2 by E1, right, from this. Okay. So, let us compute I1 for this problem, which is going to be 10 into 50 cube by 12, which is 1.04 10 power 5. Let us compute I2. This is the second member, this is the first member. 20 into 100 cube by 12, which is 1.67 10 power 6. Okay. We say the total moment of inertia I is I1 plus I2. Let us neglect the I from member 3. This is member 3. Okay. So, let us say E1 by E2 is 1.67 10 power 6 by 1.04 10 power 5, which is 16.058. Equation, let us say 8. E1 plus E2 is H, which is, okay, we will say this is 80. In this figure, this is anyway H, but we have this dimension, okay. This dimension, the clear dimension is 80. So, H will be now equal to 80 plus 5 plus 10, which is 95, equation 9. So, by solving these two equations, I get E1 as 5.569 millimeters and E2 as and E1 as 89.431 millimeters. That is a simple illustration what we had to solve this problem. Okay. Friends, in this lecture we learnt more about the concepts of shear center, we also did a numerical example. Okay. We derived the equation for shear stress, then we did a numerical example of an I section to locate the shear center. We did this using first principles and the derivations are very clear, therefore, there is no question or any confusion on this, right. So, friends, we will do couple of more examples in the coming lectures to illustrate about the calculation of shear center more in detail. We will also take up shear center for unsymmetrical sections. We will try to elaborate this more on coming lectures. Thank you very much and have a good day. Bye.